I mean, many people have wished I had a mute button. Oh dear.
So good morning, everyone. Have you all had some coffee? Yes. Are we all awake? Yes, good. Okay. So my name's Zaid, and you might recognize my name just from some of the emails you might have gotten. But first, I want to say thank you for all of you for coming today to our first BioDev Network conference. And this is all about explainable AI. So we're going to kick off with some pre-conference workshops, and the first one is going to be led by Jack Fraser-Govil. And he's going to be leading you through some activities this morning. This is going to go on to about 12:30, and then we'll have a lunch break. So I'll hand over to Jack right now, and hopefully everyone online as well can hear this too.
Thank you very much. So first things first is there's a bunch of resources that we're going to be using throughout this workshop. You can either clone them locally, which apparently is taking a long time because apparently I put too many images on it, or you can just access it online through the GitHub Colab, which takes you to a collabs version of everything. There's also going to be some interactive questions by Menti with this code, so join that and we can have some fun. Yay. So the remit of this first workshop is going through the first principles of machine learning, which I've given the lovely subtitle of A Peek Inside the Black Box of Machine Learning. And the reason for this is because this is an Explainable AI conference, and in order to explain why machine learning, these mysterious black boxes, give the answers that they do, it's first necessary to understand how they're giving the answers that they do before you get to the why. So I'm going to just potentially call some of you out directly, because if this seems familiar, does that seem a familiar thing for most people, their experience with AI? No, you're all experts. None of you have ever used an out-of-the-box toolbox before. You've all written everything yourself. This is interactive.
No, I never used it.
You've never used it before? Oh, wow, you're jumping in at the deep end. So, most people, when they do machine learning, will use some kind of out-the-box toolbox, which is, your PyTorches, your Keras, your TensorFlow, all of these kind of things, which are great. They work, they let you access incredibly powerful tools, but in doing so, they sort of smooth over some of the internal logic and some of the internal workings of how these tools work. And our goal today is to write a machine learning feed-forward neural network, fully trainable, from first principles without using any external libraries apart from NumPy. We'll be using Python for this. So I'm going to walk you through from first principles, starting from the initial work on machine learning in the 1950s, all the way up to, by the end of the session, you having a thing where you don't have to rely on something somebody else wrote, and you can say, yes, I understand that. Sound good? Everyone's excited? It's early, isn't it? Right. So as I said, the aim for today is we're going to work through the classic perceptron. We're going to write your own, train them. We're going to work on feed-forward neural networks, which will not work when you first do them. Then we're going to discuss why that is, what you have to do to get them to work, and then we're going to do the big job of training them on a custom data set. And by the end of it, you will have a network that you can call and run yourself, and in principle, do any kind of machine learning task that you would care to do. We will see why that is a terrible, terrible, terrible idea. But in doing so, I hope that we'll learn something, and you might get some insight into some of the questions and things that we raised over the course of talking about explainable AI. Okay, I am a theoretical astrophysicist by training. I do maths. I do lots and lots of maths. There will be equations. You will need to more or less know what they mean. I did write a big, long document called Notes, which was meant to be sent out beforehand. I don't think that happened, so there are pointers in the lecture, in the slides, which will point you to sections in the notes if you are completely baffled by what an equation is doing. If you come away from the end of today going, I wish I understood more, read through the notes at your leisure. Otherwise, we're just going to have to sort of smooth over some of those gaps. But I'm hoping we're going to explain the maths in a way that you'll be able to understand. And the entire purpose of today is to try, fail, and then learn something from it. So if you don't understand something, throw a hand up. I've got some helpers around the room who might just say, please ask Jack. But today is about trying, failing, learning. So let's start off with the perceptron. The perceptron was the first sort of foray into machine learning. And it's a good indicator of how machine learning is actually incredibly simple on the face of it. Because it was developed in the 1950s, pretty much as soon as we had computers, we had machine learning, which raises the question of why it's taken 50, 60 years for it to come into the mainstream. But hopefully, by the end of the day, you'll know that answer. So the perceptron, I'm going to explain via this graph. It is the single most controversial slide I have ever written, because I do not classify the whale as cute. I heard no, whales are regal, they are noble, they are not cute. So, as a human being, if you were to ask to classify which of these animals is cute based on their size versus their amount of fur, humans would quite obviously just be like, yes, rabbits, cats, dogs, cute. Naked mole rats, eyes, not cute. Mice, controversial, I think they're cute. They're cute when they're not in your house. And I think we would all basically recognize that the delineation is that line there. For now, I'm going to say that that is the line that separates cute from not cute. And that, more or less, is what a perceptron does. A perceptron is an algorithm that draws a line through a plane and says everything on this side of the line has this label. Everything on this side of the line has this label. That is machine learning. Hooray. So obviously it's a little bit more complex than that. In order to split the plane into two parts, you need a line. And obviously this is in 2 dimensions. I've got 2 dimensions input. I've got size and fur as my inputs. I could also include teeth. I could include rarity. I could include all sorts of things. But for now, we're going to stick to a 2D example. So I need to define a line. How many numbers do I need to define a line? What's the dimensionality of a line? 2. OK, you're right. Oh, there's a slide. I need n. In n dimensions, I need n numbers to define a line. You're all familiar with this in 2 dimensions, hopefully, because it's y equals mx plus c, which everyone can chant just from memory from high school, right? So let's bear that in mind. In order to define a line, we need 2 numbers. OK, the perceptron takes this form. You get an input vector, so this x here would be a vector with the size on the top, and it would be the furriness on the bottom, so this would be 3, 6, I don't know. Then you compute this, and if you don't know what a dot product is, speed read notes. You compute this value here, and if the value is greater than 0, cute. If it's less than 0, not cute. That's all it is. It's a dot product. People will be familiar with this formalization. I'm actually going to write it a different way. I'm going to write it in this form. I'm not going to include what's called the bias. I'm going to basically make my vector 1 bigger. We'll see why that is later. They are exactly equivalent. So how big, and W are what are called the weights. How many numbers are in W? I'm looking at you. You gave me your answer earlier. So x is a 2-dimensional number. It's got size and furriness. I've added 1. So x tilde here is a 3-dimensional vector. It goes 1, size, furriness. How big is W? 3. It has 3 numbers. Dot product is, when you do the dot product, you take, I'm not going to, you basically line your vectors up next to each other, and you multiply and you add. So W and X are the same size. So if X is 3, W is also 3 dimensions. Why do I need 3? Over here, he told me I needed 2 dimensions to define a line. Why do I suddenly need 3 in my perceptron? I asked this deliberately because I looked online, and all the answers I found online were horrifyingly wrong. Any guesses as to why we need 3 numbers to define a line? I think you might have a hint. It has nothing to do with the bias. If you look online, everyone will tell you the answer is because of the bias. And they'll say this because when you define your line, you need to be able to move your line up and down to be able to meaningfully do it. And the bias term, when it's written like this, the bias is the term that moves it up and down. That's not true. That's why you need to write it like that, but it's not why you need 3 numbers. Because if it was the bias term, we just write it as mx plus c. I wouldn't do a dot product. I would just say, my line is mc, and I compare if y is greater than the value. I'd still only need 2 values. I wouldn't need to do a dot product. The reason I need this is because, in this formulation, this area of the curve is always above the curve, and always has label 1. This area is always below the curve, and always has label 0. But what happens if all my cute animals were here, and I wanted 1 to be cuteness? They'd never, ever be able to work. The perceptron would always say, nah, anything in this area is not cute. The problem is, we don't have directionality, which I think is what, there was some sort of, the problem is that we need to be able to define which side of the line is which, not just split the plane in 2. We need an additional bit of information, which is, are we looking above or below, which is where we need this additional number. So that's why we do the dot product. So in this formulation, this is the exact same line, specifies the exact same line as between here. But if I now swap this +1 for a -1, oh look, suddenly I can call animals here cute. That is why we need 3 labels. So everything has 1 extra dimension than you might naively think it would. And it's precisely because we don't know a priori which side of the line we are looking. We need some kind of additional information that can leak into the system so that we can say, okay, that side of the line is cute, rather than having to, when we set up the problem, say, make the decision, given the whole point of machine learning is to let the machine do as much as possible. So that's just a bugbear that I had, because I looked online and everywhere was wrong. So having said that, we're going to go on to the, oh, actually, I'm going to go and do the interactive session first. Okay. Has everyone joined the Mentimeter? If not, scan the code, enter the, and keep this open as a tab. So the way that this session is going to work is we're going to go through, I'm going to talk, then I'm going to shut up, and you're going to have some blissful silence. During those periods of blissful silence, I'm going to give you some tasks where we will try and implement the knowledge that you've learned while I've been talking. As we go, that will mean you gradually build up this toolbox of machine learning. The first task, as you saw, is going to be to write your own perceptron classifier. This is all based on the Jupyter notebooks that were in the Git that I asked you to clone earlier. Hopefully, we'll then be able to walk through and you'll be able to test these things. The task will get progressively more difficult and more involved. But you will also learn more. Okay, I can see I've got 20 people, so I'm just going to give you a little while to log into that, and then we will do some quick preliminary things that I forgot to do earlier, and then we will move on to the first task. I'll also do some questions because I'm seeing some blank looks.
Just to repeat, we need 3 dimensions because we don't know which side
Yes.
of the graph we are looking at.
Yes.
If it's not on the line. But what does the 3rd dimension represent?
It's a good question. So in this plot here, this dimension represents the verticalness, this dimension represents the slope, and this dimension represents which side of the line you want. If this is negative, it's this side of the line. If you're positive, it's this side of the line. It's all a bit muddled in, because actually, you've got this prefactor, so actually everything's all a bit muddled in, because technically you would have a number here and you'd have to divide through, and everything affects everything else, which makes it less easy for humans to understand unless you write it like this. But it has an additional benefit, which is that actually when it comes to optimizing it, it means that if you're gradually changing these values, you don't have to jump wholesale from -1 to +1. You can gradually change all of the numbers and the line will gradually pivot around. So the 3rd dimension is doing 2 things. It's telling you which side of the line you're doing it. It also lets you gradually change it rather than jumping from one to the other. Otherwise it would be chaos. Because every time you changed anything, it would completely change the classification line. Does that answer your question?
Yes, so the values of the 3rd dimensions are not only +1, -1, but also the...
They are, so the values of the 3rd dimension can be anything, and it won't change the line, or whether it will change the line by a multiplicative amount. But all that matters for where the line is whether it gives them a bit of leeway to move. Otherwise, you change one thing and everything would... You know when you're writing a presentation on Microsoft Word and you move an image and everything jumps 6,000, this means that doesn't happen. It's a sort of softening parameter almost. There you go, very pleased with that analogy. Okay, I can see I've got 30 people. Let's get going. So, how do I go to the next slide? I click the next slide button. Okay, just for my own benefit, I'm just going to rate how confident you are in each of these areas. From the left-hand side, 1, never heard of it, to I think it's 5, which is yes, I know exactly what this is, I know exactly how to use it, I use it every single day of my life. Just so that I know quite where to pitch where we're going. Oh dear. If you click 1 on everything, I'm really going to suggest that you go and speed read all of the notes. Right, somebody's clicked that they know what Yang-Mills theory is. You are a liar. So what I'm getting from this, just while we're going through, is it looks like people are roughly happy with differentiation calculus, less happy with the chain rule, which is odd because it falls under those two rules, but hey-ho. And correctly, nobody knows what Yang-Mills theory is because that is a theoretical physics construct that is way beyond my pay grade. Okay, so yeah, it looks like we're all sort of vaguely happy, but not necessarily experts, so good to know. Okay, so this is the challenge. Spoiler alert, the answer's dog. So your goal for now is to open up the notebook, the Jupyter notebook, which is called XAI Workshop in the GitHub, and to fill in the prediction method of the class structure that's given there, and just run it through on the data, the cuteness data, which is, unsurprisingly, these guys. So this is going to be sort of our easy test bed of data sets that we're going to use for the first half of the session. So if you go into the notebook, you'll see something that looks like this. And you'll look something like this. I've given you some code that loads in data, some things that plot data. There you go. There's a slightly truncated form of the plot that you saw earlier. And then your goal is to fill in this method here, and then test it and find out which of these data is currently classified correctly by the perceptron, given that I have given you a set of weights to use earlier. So while you're doing that, I'm just going to wax lyrical about the sort of purpose of these notes. So these notes are going to be you writing your own machine learning network by the end of the session. I appreciate that's quite a big ask, especially as I'm going to be throwing some maths at you that you might not necessarily understand. I hope that I've managed to write the tasks in such a way that you can follow them through individually and solve each of them and then iteratively feel like you've understood something. If you get stuck, there are a couple of helpers around the room. Helpers, throw your hands up. There was a third one. There you go. They should be able to help you, or at least store your questions to give to me. And if you get really, really, really stuck, there is a separate directory called hints, which has a solved version of this notebook where I've written all the code in and it all runs perfectly. So, you could open the solved notebook, click run all, finish all the tasks and walk out. Congratulations, you did everything in 15 minutes. The goal of today is to try and write everything yourself so that you feel like you've understood something. So only look at the notes, the solved notebook if you are really, really stuck. And if you do, hopefully, just look at it, understand it, and then go back and try and write it yourself. Don't just wholesale copy and paste things, because, again, if you wanted to wholesale copy and paste and use things that already existed, then you'd just use PyTorch. So, and then once you've got your thing working, there you go. Press enter to hide correct answer. There you go, that would have been useful. We'll say another 6 minutes. I'll also hold a straw poll as to which of these animals is the cutest. If anyone doesn't say the cat on the end, you're meant to leave, because that's my cat. His name is Checkers, and that's him on his birthday. just to give you a hint, just to get things moving, this is the sort of thing that you should have written. So I've done this through augmenting the vector. So because W is of size 3, your input vector is of size 2. If you'd have peeked inside the data vectors, they are all two-dimensional vectors. So you need to do something to make this vector bigger. I've used NP insert. Then you take the dot product, you compare if it's greater than 0, and you return it. So that's all this function should be able to do. Is anybody absolutely baffled by what's happening here? Please throw your hand up early. Yes. What's the matter? Trick here is the augmenting, is the bit that might not necessarily be obvious, which is the whole including the bias into one big vector. And the reason we do that is basically it makes the notation horrible for now. It makes the notation a lot simpler later on. Is why we're bothering to do this. So you've got that written. All you have to do, sorry, I keep on going quiet, and then the microphone people are being very baffled by me. Once you've got that, all you need to do is then you need to loop over the data, which is provided by the function you got. And if you do that, and I have not got my kernel set up, so it's not going to work, because it hates me. The person who said that my cat is classified correctly is wrong, because my cat is classified as not cute by that perceptron. So that's right. That's right. I'd rather questions than absolute silence.
I managed to see.
Yep.
To say, I mean, the ones over the line.
Yep.
So in blue are the cute ones.
Yes. So that's.
The cat is cute.
But that's the line that I told you. So
Okay.
this vector here defines a different line.
Ah, okay.
So.
But now how can I execute this one?
Okay, so you do something like.
Okay. For that and that.
Something like that. It's difficult to write on other people's lap. Perceptron. Something like that.
Okay. That was very easy.
Yes, I've done a very complicated way of doing the prediction, but once you've got your perceptron that's written like this, all you need to do is you can't type when other people are watching. P.predict data I. Something along those lines. So all I've done is I've made my perceptron object, I then loop over the data, make a prediction, and I compare it to the labels which were in the input in the loaded data set. Although actually, to be fair, for this task, I should be doing that. Here we go. So let's load my data. Yes, please do that. No file found. Okay. There we go. So, looping over the data, what you should find is that the dog is the only animal that is classified correctly. And if I run my more advanced, that's because I've taken it apart. There we go. So, this is what the weight vector that I provided for you looks like. The blue line is the line that is specified by y equals 1x plus 1, which is just the gradient 1 line with intercept of 1. And nominally, it looks like it should classify everything correctly apart from the dog. But actually, it classifies everything incorrectly apart from the dog, and that's because, as we talked about earlier, the direction of the line is wrong. Because I've got a -1 in my final element of my weights, which is all the way back here, this -1 means that my line is looking under the curve, not over the curve. If I were to change this to a +1 and run everything again, oh, no, that didn't work. Well, this is because everything changes. Why didn't that work? These possibly need to be -1s. There we go. Now they're all correct apart from the dog, because I changed the direction of the line.
Can you show us the code how to call the perceptron?
I just got rid of it, unfortunately. It was something like that, but I can't type while other people are watching. I get nervous. So having said that, I'm going to, if you haven't got it written, go and copy in the code from the solve notebook, because I'm going to move on to the next stage of things, which is obviously, that was terrible, right? Everything but the dog was wrong, because I gave you some weights, and I'm a meanie, so I gave you bad weights. So the question is, well, there we go, let's go back to where we were. A perceptron is only as good as the weights, and this is true of all neural networks. They are only as good as the weights that you use to make the classifier or make the prediction or whatever. So the key thing, the single most important thing, is the training, which is the neural network way of what I call optimization and numerical optimization. So training a perceptron. So you are given some weights, and you want to try and make them better because you want your classifier to predict things correctly. So the moment you loop over the data, you made a prediction, and you compared it to the truth, and then you throw up your hands and went, well, this was bad. So what you need to do is you need to update your weights based on how wrong your perceptron was. So if your perceptron makes a correct prediction, you don't need to do anything. If it says that dog is cute, and your data set says that dog is cute, then you're golden. If it says that cat is ugly, then you need to burn it in fire because all cats are cute. Thank you. Audience of one. So this is the formula for updating a perceptron neural network. So your weight vector is updated to this new form, where this is the old weight vector. We'll come back to this. This is the truth. This is your true label. This is your, why am I pointing with my fingers? I've got a laser pointer. And this is your prediction, the output from your perceptron network. And this is the input vector. It might be a little bit strange why this appears here. If you, in the lecture note, or the presentation notes, go into lots of detail about why and how this improves your prediction. The long and the short of it is, if your prediction is wrong, it means that T and P are not equal. Fairly obviously, that's how we're defining wrongness. What you need to do is you need to nudge your dot product back towards 0. Because if way greater than 0 and it should be less than, then you need to make it smaller. If it's currently predicting that it's cute when it's not, that means that it's very negative, and you need to push it closer to 0. What this algorithm does is it pushes the dot product back towards 0, and therefore where the decision point occurs. So if you do this formula, so you do it on the data point, so you evaluate this for cat, and then you use that to make a prediction about dog, and then you update it, and then you use it to make a prediction about a warthog, and then you update it, and you just loop through your data, and you keep on going until either the sun explodes, or you get bored, or it works. Does that make sense? So again, what this formula does is it just updates your weights to make them less wrong. If it is wrong, if it's right, it does nothing. If it's wrong, it tries to move it in a direction that makes the weights correct. Works because it makes the dot product move closer to 0, and hence the tipping point. Task 2, unsurprisingly, using the perceptron that you now have written, implement that training algorithm, which I'll put back on the screen, and then apply it to the cuteness data. And the presentation thing is, how many full loops through the data does it take to train to 100% accuracy? So I'll put that formula back on the screen. So again, so just back into the notebook, what you want to do is you want to go into this training function, and you want to put that formula in. And then you need to do another loop over your data, and just call that function again and again and again and again until you are happy. And then run your same check, and then hopefully your line should be different. Is everybody happy with that task? Can I have some noise? Is everyone happy with that task? Yeah. Again, if you didn't manage to get your perceptron to work, then just go into the hints directory, steal the perceptron that I already wrote, and use that so that you don't get left behind. Oh, thank you. I completely forgot to talk about R. Duh. Right, so R here is what is a word you're going to come to loathe, is the learning rate. So the learning rate decides how big the step should be. It decides how much it should nudge it back towards 0. If R is 0, it does nothing, because your weights get updated to the weights, which is great. If R is tiny, you take tiny little steps. If R is massive, you take great galumphing steps, and the line will start flipping and turning and doing all sorts of crazy things every time it updates. So the big challenge with all forms of numerical optimization is choosing what R should be. If R is too small, it takes 1,000 years to do anything. If R is too big, nothing gets done, because it will just... So I recommend R about 0.1. For the challenge, 0.1 is the key value. You can go smaller, and it will not overshoot. So with 0.1, it will overshoot, and it will keep flipping, but it will converge. With 0.01, it will very slowly converge. But try it, experiment. I saw a hand go up over here. Hello.
I think that works, so keeps not working. And it kicks me out.
I get kicked out regularly, and I work here, so. Got network problems over here. I'll delegate that one. Happy, happy, happy. We happy over here? We know what we're doing?
Yes.
If you give this data, how was the data decided that it should be 1 or 0? Was it you decided that?
Yeah. Yeah, for those of you who are wondering, the final arbiter of whether an animal is cute or not is me. I'll come back to that when we discuss functions and things later. But for now, you're trying to predict whether I think it's cute or not. which is why whales are not cute. And then once you've got your network trained, time how long it takes to go through the data, and then give your answer on the Mentimeter. Full epoch.
So one epoch will contain all the samples.
Yes, not doing batch training yet. I've caught someone out. Someone here has put 68. That's the answer you get if you run the data in the solved notebook without altering it. Yes, I'm mean. How are we going over here? Are we understanding what's going on, or are we completely lost? That's all right.
I think this is the lost side.
What's the matter?
So many things.
Related to this presentation. we will go.
So I kind of get this. So the input only it's two-dimensional, right? And
Yes.
You have to add in.
Yep. So this is doing if you give the entire data set.
Yeah.
This basically says. I'm turn my microphone off rather than me broadcasting this conversation. Okay. So this section of the code, all it does is it says if this is a list of inputs, it breaks it apart and calls it, which means you can either give one data point at a time, or you can give the entire list. It's needlessly complicated. So the important thing is this bit, which does the insertion. So actually, let's do it. This bit is more, again, I wrote a version and then I made it less complicated. This is a Windows machine.
Sorry.
Yeah, Windows machines. I used to hate, oh dear, what have I done? So this augments the vector because it's one dimension too small.
Yeah.
We do the dot product with the weights.
Yeah.
Then we compare it's greater than or equal to 0.
Yeah.
So that's all the perceptron does.
Yeah.
You happy with that? What's gotten you out then?
The next bit.
Okay.
So I'm not really sure how to then convert. So this is obviously using a rate. You're going over it and trying to improve it basically by correcting each time using the rate vector, but I don't know how to then apply that into like actual code.
Okay. The trick is that it's down here.
Oh, okay, that might help.
Yes, we're going to notebook solved. So I duplicated everything again, just because, yeah. So this is the training here.
Right,
So I pre-augment all the data rather than making everything. And then let's just get rid of that. So the important thing is I make a prediction.
Yep.
So I loop over a number of steps.
Okay.
Then I loop over each of the data points.
Sorry, it's
That's all right. That's why I keep fucking
yeah.
So then I loop over each of the data points, make a prediction, and then this is rate times the labels minus p, which is the formula that's now covered.
Yep.
And then I do update is the update size times the input vector. So this is just implementing.
So it's doing the separate parts.
Yes, I do. So I do r times l minus p, and then times the vector separately, just to make things easier.
Sure.
And then we just add it in.
Oh, okay.
So it is, yeah.
Okay.
Is that helping? I realise I've just explained everything in parts, but I hope that's made it clear.
I think so, yeah.
Cool, cool. Yes, if you're looking on the solved notebook, the training is given in the next cell down where I've duplicated everything, just so that the solutions are given completely. We've got some people who've trained some networks. How's it going over here? Good.
Thank you.
Is it going all right over here? Working? 12, yeah, no, that looks good. I got 11, but it depends whether you count the final one or not. Because if you do the check where you don't move anywhere, does that count? I gave 10 to 12 as the correct answer, so you're already good. Yep.
I mean,
That's right.
yeah. So I was just looking at the idea of what we are
Yeah,
doing.
that's exactly what you. Yeah.
Because we had the wrong predictions.
Exactly.
Basically, we are trying to train our model to see if how many tries to get the right prediction.
Yep.
Right. So I mean, where P coming from? That is 0 or 1.
Yep.
But that is coming from the prediction that
Yep.
you made earlier.
Yes. So this.
Okay.
Wherever. Yeah. This
yeah,
predict here.
Yeah, I got that. So that is getting, and then so you have given a slow rate that is 0.1. Is that?
Yes. Yeah. So, well,
So,
I gave that to be mean, because if you wrote the code and ran the code without modifying it from this, you get 68, which, as you can see, is what that person over there has got. They got 68. So no, the whole point is, if you run this with 0.1, you get the right answer.
okay, that's fine.
Yeah. That was just to catch people out who were copying things directly. So any value will work. So try running it with 0.5. Try running it with 10.
So it just means that it takes 68 trials to get to that.
Rather than 11.
Yeah.
It all
correct.
matters. But the point is, if you use a value that's too big, the line will just bounce around and take a long time. So there is an optimum where if you put it too big, it takes ages to converge. If you put it too small, it takes ages to converge. There's a nice sweet spot in the middle.
Okay.
Okay?
Okay, taking it slowly. I will understand.
Yeah.
Everything. Okay, thank you.
If you finish that, then move on to the next task, which is applying it to a different data file, which is cuteness augmented, which has got some additional animals in it, which are things like slugs and axolotls and things. Try that and see if your nice, newly trained perceptron still works. And if not, tell me why. What am I looking for? There you go. Everything working over here?
Just figuring it out.
Yeah, no, let's.
Quite badly.
So you've got a per. I'll just uncover that. Yeah, so you're training per data. Yeah, that's fine. Why are you only training the third? Well,
I'm going for the signed.
But you don't know. A priori, you need to train the entire weight vector.
Fair enough.
Also, Python is 0 indexed.
That is true as well.
So that's going to.
That's why I'm running that.
So I would. The only thing, and this is running for each element in the data set, and then this is running for each element in the data set.
Yes, so I was going to do...
That should be
Yes,
some number.
I was going to make this a... to show the data and then do training.
The very first step.
What's the matter?
Not getting it actually.
Okay.
So we have this data.
Yep.
Taken the instance of this class.
Yep.
And then so it has just the numbers, right?
So data is you need a len, or for in data. That's just, there you go.
Okay, so it's 2.
Yes, so data is a 2-dimensional vector
And now we provide this each vector
into the perceptron.
to
Yep,
predict.
into predict. Has anyone tried it on the augmented cuteness data? No. Oh, I can see some cuteness going on over here. It's going all right?
I just didn't use to.
9? Oh, bloody hell. What's your training size?
100 iterations.
Alpha's 0.1, huh?
Quite low.
Yeah, no, you still got it on
Yeah.
training in 9. Bloody hell.
Oh, here I'm just.
Oh, 0.1.
Yeah, and 10 iterations. So
Yeah. Are you shuffling?
yes.
That would, okay. Yeah. So yeah, so try that on the...
I looked up the solution.
That's right. Yeah, no, again, as long as you understand it. You're allowed to look things up as long as you understand why it works. Okay, a nice spread of answers around sort of 10-ish seems to be the conclusion. What's going on? Ooh.
I have a bit of a silly question.
Yep.
But what is the bias in terms of training time and accuracy? And why should we not have the bias also be itself a trainable parameter?
So the bias is a trainable parameter
Oh.
because it's one of your weights. So rather than your weights being two-dimensional,
Yeah.
we've made your weights be three-dimensional.
Okay.
And basically the package is, yeah, it's just been packaged in,
Okay, fair enough.
which is why you're doing the augmentation.
Yeah.
So it just makes the notation easier.
Okay. And when this code was running in the new data set, it never really converged to a good accuracy.
Yeah. Why might that be?
Why might that be? Are there any particular features of this new data set that are different from the old one?
It's got 7 new animals.
I see.
So it's got Tasmanian.
Dimensionality.
Yeah, it's got Tasmanian devils. It's got
Yeah.
I mean, axolotl is a big giveaway. Someone's claiming to have managed to train it in like 3 epochs, which is incredible. So just conscious of time, I think we will just go on to the next step, and then we'll take a break to have some drinks and go to the low end things, and then we'll move on to the meat of the moment. So,
Why in train rate is not in the variables? Like, because I would like to change it from here.
oh, that's just, well, you can add it.
I moved it here.
Yep.
But why was not the...
Oh, because I was writing it quickly on Sunday night.
Oh.
Sometimes things are just dumb. Well, this is one of those things of, yes, in a package, then yes, you should always make it be a parameter, but... Okay, so hopefully, if you manage to run the code and run the training, you will have managed to get it to train and therefore classify your animals correctly. Let's go to training. There you go. So, and I get it after, oh, that's 66 epochs. If I put this up to 0.1, I get it up to 10 epochs. So some of you who looked into the solutions notebook might notice that I called this function here. Each time I loop over the data, I shuffle it. Why do I do that? In a more advanced neural network, that might be the case. For this case, because all it's doing, so a perceptron is guaranteed to converge no matter what the order of the data is. It just makes it happen quicker because, for example, if it's got 2 animals that are either side of the line, and it evaluates cat first, and it misclassifies that, so it moves the line, and that means it misclassifies dog, and then it moves the line, you run the risk of it just bouncing backwards and forwards between the two. And it will eventually converge, but it will just bat it backwards and forwards. So if you shuffle it, you reduce those things occurring every single epoch. So it's just a trick to make it not get hit between those two. If your data set's just organized poorly, then it will.
So it basically helps the model for the generalization of the data set. Let's say.
Yes, so in terms of stochastic gradient descent, what it means is that you don't end up being caught in artificial local optima because of the order of your data set. It's not sort of not technically necessary. If an optima exists, it will find it. This just makes it easier. That's right. So if you run it on the data set that I gave you, it will correctly draw the line between these animals. It's maybe not quite where we would have drawn the line. For example, when we drew the line in the presentation, we didn't quite have ant directly on the other side of, we drew the line sort of what's called a maximally separating line. The reason it did that is because the network just drew the first line that it got to that met the criteria. It doesn't sort of care about aesthetics. If you do things like support vector machines, which do this but fancy, then it will try and draw the line to sort of maximize the difference. But with a perceptron, all it cares about is, did I get it right? And it doesn't really care if it's right on the decision border. It's just like, great, I got it right. If you then run the data on the cuteness augmented data, which adds in a bunch of animals, and of course it didn't work because it hates me. You'll find, so I added the Tasmanian devil, the capybara, the axolotl, the slug, a panda, and a quokka, which are great animals. And you'll find, after 0 epochs, this is where we stand. After 100 epochs, this is where the line is. After 300 epochs, this is where the line is. After 600, 1,600, 1,800, it never converges. The line will just bounce around continually. It will never be able to draw a line that separates these animals. And the reason for that is because no straight line exists that can do that. This data set is not linearly separable. I have classified an axolotl as cute, because they really are. If you don't know what an axolotl is, go and Google them. They're really cute. They're like fish, but met dogs. So basically, in order to draw a line that classifies both these things as cute and also an axolotl, you need to draw a curvy line that did that, and then also threaded the needle between otter and Tasmanian devil, because Tasmanian devils are like cats with psychosis, and it also needs to catch capybaras. So you need to draw a really curvy line through this space, which a perceptron cannot do. All a perceptron does is it draws a straight line or a hyperplane or some multi-dimensional equivalent of a straight line, and then just says everything on this side 1, everything on this side 0. And if the data can't have that line, you're done. So that's the main drawback of the perceptron. Now, it is not true that perceptrons cannot do this. You'll see there was a famous paper in the late 50s, early 60s that proved that perceptrons cannot solve a certain class of problem called the XOR problem, but actually you can get around that. So if you do some fancy things with your input vector, so the problem was that I just gave it x and y. If I also give it x, y, x squared, y squared, and xy, so I give it a 5-dimensional input vector, it turns out, actually, that it can do it quite well. Non-linear dimension. I mean, it won't be great, but bear with. No, that's just another straight line, damn it. So now I've included 21 parameters. There you go. So if you include 21, and these aren't different parameters, these aren't including the length of their teeth, all it's doing is it's taking the values you have and just doing non-linear things to them. So also giving it x squared, and also giving it sine of x, and also giving it the log of x, and also just giving it sort of weird functions, it's able to draw curved lines despite it only being able to draw straight lines. And what's happening is because when you do this weird thing to the vector, where you basically just add in extra elements that are all different parameters and all this, what you do is you project it non-linearly into a really stupid high-dimensional weird space. Then it draws a straight line in that space and then projects it back down into your 2-dimensional space. So it's the equivalent of taking a piece of paper, folding it into like an 8-dimensional torus, and then cutting it. When you unfold the piece of paper, you end up with some weird curved lines. This is all basically equivalent to that thing when you were a child and you folded the piece of paper and you cut it all and you made snowflakes, and you pulled it apart and you had lots of different cuts and they didn't look like the cuts that you made. That's what's going on here. We fold the space up in a really weird way. We curve it up, we scrunch it, then we start cutting a straight line through it, then we unfold the space, and the result is a bunch of curved lines. And this works. This solves the infamous problem. All of this is great. Now, with this formalism, by making our perceptrons multidimensional and nonlinear, we can solve, technically, any analytically separable problem.
perceptron can only divide between two categories.
Yes. So at the moment, it can only divide by 2.
Even using more dimensions.
So you can do a one-hot encoding and things. So yeah, you can. It would stop being a perceptron, but it would be equivalent. So I've just said that we can do anything with a nonlinear perceptron. So why are we faffing around with all these neural networks? Why are we doing layers? Who cares? Why doesn't everybody just do this? Would help my... I mean, I can interpret this. I can see where it's drawing lines. Yeah, but I mean, a feed-forward neural network can do this as well. The answer is both stupid and dumb, which is it does work. Theoretically speaking, any feed-forward neural network, a normal FNN, can be modeled with a single layer perceptron with an infinite number of dimensions. Doing so is an absolute pain in the arse. It's just not physically possible to do this because you end up running into the limits of basically finite numerical computational accuracy. Of when you update your parameters, you take a step of length r. But if I've got a parameter that's got x to the 512, and my x is 10, then I'm suddenly computing, trying to move my parameters by a value of 10 to the 512, which is a really big number, and my vector just gets completely balked. It just doesn't work in terms of optimization. So theoretically, this does everything we could ever want, but it's of absolutely zero practical use. So that's why we have to use these more advanced things, is to basically get around this problem. There's also the problem of, okay, you could say, I'll just do it to a smaller, I won't include 512, I'll just do it to x to the 5 or x to the 4 or whatever, which is what you saw me fiddling around with here. But then that's just the user basically ends up controlling things. Can we teach our network to do this automatically? So rather than the user saying, take an input vector, map it into some ludicrous dimensional space, and then map it back down, just do it yourself. And that's what a feed-forward neural network is. When we talk about these sort of more basic neural networks, they are a way of teaching the computer to do this curvy, nonlinear, multidimensional in a way where the humans don't have to get involved. So here you go. So you can augment your vector like this, and it will, there you go, looks like that. So this is a famous problem. This is a sort of extension of the famous XOR problem. And the XOR problem basically says that a normal perceptron cannot solve, if you just have one data point here on each of the corners, it can't do it. And an infinite dimensional perceptron can get very close to solving this. So this is with 3 parameters, 6 parameters, 10 parameters, 15 parameters, 21 parameters, 231 parameters. But actually, you'll struggle to do this perfectly because if you've got sort of infinite points, it struggles with that as well. So perceptrons can do most everything, but they're not very useful. So what do we do? More. Rather than asking my perceptron to do something, we ask lots of perceptrons to do a little bit of something. And we add that all together, and hooray, it works. And that is essentially my description of what neural networks are. They are a bunch of perceptrons, each doing a little bit of something complicated, such that the whole is very complicated. So the multi-layered perceptron is the simplest form of neural network that exists. You take your input vector, you augment it with our extra dimension, and then you put it into a bunch of perceptrons. So W10 is one perceptron, take a dot product, get an output, then we do the same. Take a different dot product with a different set of vectors, then you just do that a number of times. Then you collect the output, and you call that your new vector. And then you repeat it, and you repeat it, and you repeat it. And every time, you basically take a stack of perceptrons, take the dot product, get the output, stack it into a vector, pass it on to the next layer. Okay, I want to spot anything that's gone wrong. Spoiler alert. So I will skip this stage because I'm conscious of our time. But what I would normally ask you to do is to go and code this up exactly as I've written it here, where you code up a perceptron, you stack all of these numbers together, and what you do, this is task 4, which you can have a go with if you want, but we'll take a break for now. But if you do this, randomly initialize your weights, and then I ask you, what does this look like? And as you've just hinted, it looks like this. So this is a 531 initialized network, where I've randomly initialized the nodes. It's just drawing a straight line. And that's because, as you've just pointed out, each of these operations, take a dot product, stack into a vector. That's a fancy name for doing something else. What's it a fancy name for? Take a dot product, stack it into a vector. Yeah, it's a matrix multiplication. All I'm doing here is I'm multiplying my vector by a matrix. And then I multiply it by another matrix, and I multiply it by another matrix. And I explain this in detail in the notes. What this is equivalent to is a bunch of affine transformations, which is, if you put a bunch of affine transformations together and you do another affine transformation, what you get is one affine transformation, which is a single dot product. So if I'd have got you to do that task, you'd have spent a lot of computing power, a lot of heat, you'd have wasted your laptop's batteries, and you'd have done a single dot product. Just really complicated. But the result is, if you just stack your network layers naively, you do absolutely nothing. My whole hopes of being able to distribute each of these complicated tasks amongst lots of different perceptrons is completely wasted. Hooray. All right, that's me done. No, that was a snicker there. That was a proper dad joke. So what's gone wrong? And I will leave you that question while we go and take a quick break. So go and grab some coffee, run to the loos. I'll give you 10, 15 minutes, and then we'll come for the finale of trying to assemble a network in an hour and a half. Am I talking? Oh, there we go, I'm talking, there we go. Sometimes I just like to talk to myself. Gets lonely. If I keep talking for a little bit, hopefully anybody left outside will start to make their way back in, or they've just left for good. So just to recap what we saw, just because I deliberately went over it quite quickly because I wanted to get to the break. What I said was, we've designed a perceptron that we can train. And most of you have managed to get that, or at least are aware of how they work. And I said that what we want is we want to be able to make our results, our sort of intermediary results, very high dimensional so that we can then draw curved lines so that when we unfold this snowflake, it's got some nice curvy lines drawn through it, is our hope. And I designed this architecture, I designed this personally, yes, this is Site Jack Fraser-Govil, designed this architecture in the hope that this would do this for me, such that if I trained it, I would end up with some nice curvy lines. I then demonstrated that that doesn't happen. And the reason for this is because each of these operations, a dot product and then put it into a vector, a dot product, put it into a vector, a dot product, is a series of linear operations. And as the name implies, linear means straight lines. And if all you do is straight lines, all you get out is straight lines. And that's what this, in fancy mathematical terminology, says. It says, if all you do is multiply by matrices and add vectors, which is what our perceptron layer does, you will never be doing anything other than an extremely wasteful perceptron algorithm. So we need some other ingredient. We need something that makes this work, because as the diagram gave away, this is where we're going. You all should hopefully be familiar with these sort of feed-forward interconnected neural network diagrams. What we need to do is we need to do something non-linear. And this is where the term activation function comes from. So activation functions were biologically motivated in terms of the history of machine learning. People looked at a perceptron and they interpreted that as a neuron that could be either firing or not firing. And then, maybe it's not, maybe there's sort of some intermediary layer where it's firing but not entirely. So biologically, that's where this came from. Mathematically, these things work because they break this linear relationship. Any activation function that is not multiply by a number and add a number will produce a functioning feed-forward neural network. And one of the simplest ways to make a non-linear function, so I've got a vector and I want something to happen to it, the simplest way to do that is to take a nice function and do it to each element of the vector. So this is why you'll quite often see your neural networks having activation functions attached to nodes. And there's a whole bunch of these things. There are as many activation functions as you can think of that break linearity and work. These are just some common ones that are in common usage. Now, I've said that it's a common way that we do is to basically apply a function to each element of the vector. So your perceptron does a dot product, it spits out a number, and rather than just packaging that straight away, you pass it through your activation function. So people often think of activation functions as being properties of your neurons, your nodes, your perceptrons. That's not always the case. Are there any obvious examples that people have used in the past that don't follow this rule? Softmax is the clear one. Any kind of activation function that uses information from outside the node. So softmax is one which normalizes the entire layer to basically a probability. So rather than just having, this is independent of this is independent of this, it aggregates the information, and softmax is better thought of as a function of the layer rather than of the node. But that's by the by. If all I do is I take the neural network that I wrote and I add sigmoid activation function, so I take the dot product and then I do 1 over 1 plus e to the minus x, I get curved lines. And I'm done. That is literally all we needed to do in order to unlock 50 years of mathematics. So this was discovered in the 1960s, and it's basically all you need to know in order to write a neural network is you take an architecture that looks like this, and rather than stacking them into a vector, you do some kind of weird function at this point or at this point. And you're in modern machine learning territory. all you needed to do. Why did it take so long? Right? This was discovered in the 1960s, that you need to do activation functions. And machine learning didn't really come into the mainstream until sort of 2010. They're just lazy? That assumes that we understand our data nowadays, and I don't think that's true. Yeah, I was going to say, sorry, I think you're going to... Computational power is the main problem of actually writing these things and making these things big enough. Just takes a lot of computational power. So deep learning in the 1970s and 80s was 10 to 15 layers. And if you tried to do any more than that, your computer would catch fire and your university would revoke your funding. And nowadays, we're doing transformers with hundreds and hundreds of layers and things. And it's basically not because of any great advances in mathematics or some, grand intuition or understanding. It's because our computers have gotten better and because we were able to run these functions faster. So the hardware acceleration and things is actually the defining feature. It's not mathematics. If you understand the mathematics I've written in my notes, you understand all of the mathematics you really need to know in order to do machine learning. That's a bit of a lie. Obviously, it gets a bit more complicated. But broadly speaking, that's it. All we need to do is wait 50 years for computers to catch up. And as a theorist, obviously, that's always true. The theorists are always in front. So anybody who does experimental stuff. Thank you. Again, very targeted jokes here. So I'm going to skip this function. OK. If you thought you were confused beforehand, so I've got a network, and it's a stack of perceptrons, and if we had enough time, I would get you to write it yourself. And it takes 50, 60 lines of code. It took me 15, 20 minutes to write it all up, and it works. The problem is, as I think a lot of you discovered, that requires you to know what your weights are. I don't know what my weights are. That is the big problem. That is the thing that takes the most amount of computational power, and obviously that's a very big thing to know at the moment. So, given I have a network, and I have a set of weights, how do I find the best possible set of weights? Well, the first thing I need to do is I need to define what I mean by best. And we do this via a thing called the cost function or the loss function. So this function measures how wrong a prediction is. And I'm going to move away from my prediction being a 0 or 1 and make it a continuous variable. So rather than 0 or 1, we're now outputting 0.1 and 0.9. And post facto, we can say 0.9 is interpreted as a 90% probability that it's cute. And a 0.1 is a 10% probability that it's cute. And we can interpret them this way. The reason we want this is because we want things to be nice and smooth so that we can change things by a little bit, and then things will see an effect. So this cost function measures how wrong a prediction is given a known truth value. So if I predict that a cat is 10% cute, it screams and says, no, cats are cute. And if I say warthogs are cute, it says, no, warthogs aren't cute. That's all a cost function does. It measures how wrong you are. We want some properties of this function. This function should be smooth, and it should be differentiable, which should mean if I know C, I should be able to work out what the gradient of C is. I need to know how fast it changes when I change my input value. C should be large when my prediction is wrong, and it should be small when my prediction is nearly right. And the total cost of a network is the sum of this cost function evaluated over every data point in my test set. So I assume I have some aggregate knowledge of test data where I know the answer. So this is supervised neural networks. If you're doing unsupervised, this gets a bit more complicated. But basically, this value is the current accuracy of my network measured by some function. What I want to know is what value of W make this the smallest. That is all we're doing. And this has lots of, this is called training because in neural networks we like to think of this as, we're teaching it, we're imparting some knowledge. In terms of mathematics, this is an optimization function. I'm trying to make L small by changing W, which means I need to do some calculus. Yay. Technically speaking, if you remember your differential calculus classes, what you need to do is you need to find dl by dw, and you need to solve that as equal to 0 everywhere. But dl by dw is a vector function. The number of functions is equal to the number of nodes in your network, which are very large. So I really hope you want to solve 1,000 interconnected differentiable functions. It's not going to happen. Technically, that will give you a precise answer, but it doesn't work because it can't be solved. So what we need to do is we need to find a numerical solution to this optimization problem. And what this is the answer to the question, how do you find the top of a hill? How do you find the top of a hill? You're out in the wilderness and you need to find the top of a hill. You walk uphill. If you need to find the bottom of a hill, you walk downhill. That's what this equation is saying. This equation is saying, I want to know where L is at its lowest value. So I find out the steepness, which is this dl by dw, that's what this function is, and I take a step downhill. And then I find the gradient, and then I walk downhill. And that is what gradient descent is. It is an iterative process of finding out which direction downhill is and walking in there. It's not that complicated. This method was discovered in almost as soon as calculus was discovered in the 1700s, and it is the founding basis of all modern neural network training algorithm. Is a thing that was discovered by Leibniz. So it's dumb. The reason why this is dumb, so there are more complicated methods you can use to find the optimal solution, but they take a long, long time. So this is what's known as a first-order numerical optimization algorithm. There are second order, there are third order, there are fourth order. When I was working in galactic dynamics, it was fairly common to use an 18th order numerical optimizer because we only had about 15 parameters. So you could reasonably invert a 15-dimensional matrix and do that multiple times. If I have 1,000 parameters, or rather I have 1,000 nodes, each of which has got, on average, 10 parameters, then I need to invert a 15,000 dimensional matrix every single time. And then again, your computer catches on fire and your university revokes your funding. So we use these done methods because they are less accurate, but we can compute them quicker. And it's cheaper to compute lots of these than it is to compute one of the more clever optimization routines. No? So if we iterate this equation multiple times, this is gradient descent. So all we need to do, he says, all we need to do is find out what this is, which is the rate of change of the accuracy of my network as a function of one of the nodes. So if I change the weights in one of my nodes, how much does that change the accuracy of my prediction? And I find that, and then I go and ask that question about a different node, and I ask about a different node, and I do that 1,000 times, and then I'd make a step. So in principle, again, this is a recurring theme. In principle, very easy to write down. In practice, much harder. So here are some equations. So each output of our neural network is the dot product between a node and the input vector. So I've given these lots of fancy labels. So x of L minus 1 is the collected stacked vector from the previous layer. And WLI is the ith node in the current layer. So this is just a fancy set of labeling and saying, I'm looking at one node, and I'm taking the dot product, and it gives me this value. And then, as we said, we then do an activation function on y, and then we stack that. But for now, we're just looking at y. The chain rule, which I think 2.7 out was our average score of people who are comfortable with the chain rule. The chain rule then tells me, so I'm now looking at C rather than L because it's easier, that I can do this equation. So again, this is what I'm interested in, because if I know this, I can work out what dl dw is, because I can just add them together. Because, see, there it's just summed. So the cost of one data point is equal to the gradient of one data point. The gradient of all data points is equal to the sum of the gradient of each data point in turn. So rather than having to compute the gradient all at once, I can compute the gradient per data point. So I compute the gradient of a cat, and I compute the gradient of a warthog, and then I add them together, and I have the gradient of a cat and a warthog. Nice property of derivatives. Anyway. So this is the change in the accuracy of my cat prediction as a function of one of my nodes. And it's equal to the change in the prediction as I change y times by this vector. This doesn't look like it helps. It does, because dc by dy is a much nicer entity. So, what's this? The next step is where the witchcraft happens in what's known as backpropagation. So, remember, this is what's going on. So, y is this dot product of the previous layer's inputs. So, that, and how the biologists in this corner are feeling really happy. What this says is the rate of change of my unactivated nodes as a function of the previous layer's unactivated nodes is equal to this function, which is the derivative of my activation function. And given that you wrote your activation function, presumably you're going to choose an activation function that you know the derivative of. If you don't, that's on you. Choose an activation function that has a nice derivative. And if you know your activation function, you're going to know your derivative, or rather, you're going to hope that somebody else has written it for you, multiplied by this element of this vector. Basically, the derivative is two things you already know, because you know this, because it's the current status of your network, and you know this because you're not an idiot and you chose a good activation function. And if you know this, then you can use the chain rule again, and this is the dark arts of neural network training. This says the rate of change of my cat prediction as a function of this random node in my network is equal to the sum of the rate of change of a random node in the layer above multiplied by this value that I've just told you already know how to count. So you take a node in your network, and you work out how much does it change as a function of this node that's higher up in your network, and then you add it to how much it changes this node, and then this node, and then this node. And all you do is you just work out how much does this change, and how much does this change my final answer. And you multiply those things together, and you add them all together. It's crazy that it works. So just to recap, and my clicker stopped working, because I realized that this was a whole bunch of mathematics. If we know this value here, we can update our weights. If we know this value, which is, so this is the rate of change as a function of my entire data set. If I know the rate of change of each of my data points, I can work this out. If I know dc by dy, I can compute this, which again, you'll see what's going on here. If we know the derivatives of the one layer, we can work out the derivatives of the next layer down. And if we know the derivative with this, we can work out this. So if we know the final layer, we can work out the second to final layer. If we know the second to final layer, we can work out the third to final layer. If we know the third to final layer, we can work out the fourth to final layer. If we know the fifth, and you can see where this is going. There was one missing ingredient. So what's the missing ingredient? This thing here. Because if I know this, 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 and I know this. And if I know those, I know that. And if I know that, I know that. And if I know that, I can update my weights. That's the magic. I'm seeing lots of blank looks, which is good, because this is crazy that this works as simply as it does. It turns out that when you design things to be simple, they end up being simple. The algebra itself is very, very complicated, but the final equation ends up being somewhat nice. This is all you need to do for backpropagation. And this looks horrible and complicated because it's got lots of labels. It's got I's and J's and P's and Q's all over the shop. But those are about labels, about making sure you've labeled what you've got properly. Each individual function is very simple. So again, what this says is that this function is equal to the derivative of your cost function, which is something, again, you chose your cost function. Hopefully you chose, oh, sorry, I shouldn't point lasers into the audience. If you chose your cost function, you chose your derivative. And if you chose your activation function, you know the activation function derivative. So at any given time, you can compute that. This is some complicated index of one of your weights. It's one of your weights vectors, multiplied by a thing that I've just told you already know how to compute, multiplied by a thing I've just told you already know how to compute. And you add it all together, and you multiply it all out, and it just works. So again, I appreciate I'm very much skipping over this. The notes that I've given out go over this in a lot more detail. I don't quite have time to give you a full first year course in vector calculus. But in short, this is a series of chain rule operations. It's a series of working out if x changes y and v changes x, then how does v change y? So basically, it's just a bunch of different sliders that change how these things operate. And again, all very complicated because it's all very precise as to which thing changes which, but it's just on making sure your labels are correct. If you get your labels correct, this is all very easy to calculate, as you'll see in the code. Who's confused? I am, and I wrote this. So you're more clever than me, good. So the important thing here is that this is easily understandable by people who are familiar with vector calculus and who have studied it up recently, which I haven't. So the point is, very, very complicated, but all it's doing is it's finding out a way to compute your gradient. And once you have your gradient, you can update your weights, which uses pretty much the exact same formula you use for updating your perceptron weights. Which means that the perceptron is also the solution. It's just complicated because you've got lots of different things stacked together. So, this is the final thing for today. You are going to go and write me a fully trainable backpropagating neural network. You have an hour. I appreciate that's a big ask. So what I've done is in the notebook, I have given you this. This is a series of class structures for a cost function, a node, different kinds of nodes with different kinds of activation functions, a layer, and a network, each with a bunch of very helpful functions. So your job is to go and fill in all of those methods. It's about 400 or 500 lines of code. So rather than making you do that by hand, I have given you this file here. What it has is it has all of the member functions, but I've given everything utterly unhelpful names. I've given all the member functions just random names. I've given all the member values random letters. So rather than having to write everything yourself, you're going to have to put together this jigsaw yourself. You need to read the functions, work out what it is they're doing, and therefore where they go in this class structure that you've been provided here. Once you've done that, and if you give everything the correct name, and you understand it, this will run a neural network for you. And in doing so, I hope you understand what's going on. So for example, you don't need to know how to run a backpropagating chain network. You just need to look through these functions and work out which one looks like it does backpropagation. Or rather, do everything else, and the one function that's left over is probably the one that does backpropagation. I will point out, I fed this file into ChatGPT and said, what does this do? And again, this is utterly unhelpful naming conventions. And it got it. First time, it was great. It completely reformatted it. It wrote the code structure. Don't do that. Don't let ChatGPT do your homework for you. But just as a point of order is that this can be done by a machine learning network. So my question is, are you cleverer than ChatGPT? Yes or no? So have a go. There's a version of this which has got some hints. There is a file called Jigsaw Hints that's got some slightly more helpful comments and names given, which should help you put these things together. Once you have that, then train your network on the data provided. If you finish it early, there's lots of different cost functions you can try and experiment with how that improves it. And again, the point of this is you have a neural network where you can see each of the moving parts. There is nothing hidden here apart from whatever's going on in NumPy, which is a single dot product. So take it apart, experiment with what works and what doesn't work. Ask questions and see if it works. There is another function. There's a function called complex classifier, which is a big data file. It will take quite a while to train. But if you can do that, then you will have completed everything that I wanted you to learn from this session. So have a go, and give me a shout if you're getting stuck. But in doing so, I hope you understand that all of these toolboxes that you are given, that everybody uses, people use PyTorch unthinkingly. They just add layers and it all just works. I hope by being able to see each of the individual moving parts, you'll begin to appreciate what the challenge of explainable AI means, because we designed this with one very particular goal in mind. I said, I just want to throw this thing up into a high-dimensional space and let the algorithm work it out for me. And obviously, with explainable AI, we're trying to interpret what it's doing when it's doing that. You know, what does explainable AI mean is a question that I think is going to be asked a lot. But in terms of this, I think it makes it obvious that explainable AI is a very hard task, because what's going on is just a bunch of dot products, activation functions. It's just a bunch of maths that is designed specifically to be flexible. It's designed specifically so that I don't have to think about it. So trying to, after you've trained this, trying to imprint knowledge back onto that network and say, so why did it do this, is a very difficult task, because you designed it so that you didn't have to ask that question. Right? If I wanted to be able to have very fine control over how the network predicted, I would have gone back to my multi-layer my nonlinear perceptron, where I could control, this thing here, where I could control what combination of parameters it was doing, and I could go and directly access what it was doing. But the whole point was I didn't want to do that because it made everything very difficult. It made it not feasible practically. So if you have a very good idea of how something should be being done, you have to encode that into your neural network architecture. If you're using something as general and flexible as the code that we're going to be dealing with here, you have a lot harder of a task ahead of you in working out why it's making the decisions it does. And I hope that's a lesson that you take going forward into the rest of this conference. So have a go at writing your own neural network. I hope it's informative. All right, go. There's a lot of trip hazards around here, isn't there? Yeah.
I think that's probably best.
Yes, because I've got some more things I want to talk about at the end. Well, actually, no, leave my mic off for now, but yeah, sorry. On me, off electronically. Okay, everybody. So I appreciate you're all in the middle of this, but I have wildly misjudged how long this would take. So I'm going to leave this as homework for you. So there's a whole bunch of notes in the Git repository for you to pore over at your leisure. I really do encourage you to keep on trying and understand what's going on, even if you just open up the Solve notebook and try and tease out what on earth I did. So, you know, this isn't, I'm not saying you failed, you didn't finish it in the time, because this was a difficult task. Partly I wanted to appreciate quite how difficult this was, and quite how much clever maths these pre-built libraries are doing under the hood. But I think, from wandering around, I think there's a lot of, people seem to have an appreciation for what's going on, even if you don't actually intuitively understand it. So I just want to talk about a couple of minor things at the end. Ooh, there's a picture of my cat. So if you did get your network running, and you run it on the original cuteness data, you find that it draws this line. What was my network look like? This is a 8.1 layer. So actually, it's somewhat surprising to me, at least, that this did draw a straight line. This could have drawn a wibbly-wobbly, curvy-wurvy line, and it didn't. It drew a simple straight line. But, you know, sometimes these things happen. And that's a point I'll come back to later. If you use it on the augmented cuteness data, this is what sort of output you look like. You start having to use more layers, and it starts having to actually make use of the non-linearity features. And you can see that it's drawing weird isolated islands. It's correctly identified the capybara as cute, and things like this. But my question is it true that this here is meaningfully blue? So blue means that it's assigned this point cute, red means that it's assigned this point not cute. Is it meaningful to say an animal here is cute? Right?
There's no data training in that area, so you have no idea.
No. I have no idea. Absolutely no. But my network works, so I claim that it's learned something, but it hasn't. I mean, you might say that this is overfitted, but if I could stop it early and it hasn't fitted anything. The problem is your predictions are always fundamentally limited by the data that you input. You can chuck more data in, but you still have no idea what's in between the gaps of your data. Your training is all conditioned on your data. As soon as something that is not inside your training data happens, all the bets are off. So this comes back to the fundamental principle upon which these networks work. So in 1963, I'll just Google it, XAIB24 proved that a neural network with sigmoid activation nodes of infinite size is a universal approximator. What this means is for any given function, any function you want, like whether it's me making up whether it's cuteness, I could arbitrarily decide I think eyes are cute. And there is a neural network somewhere of some size that can approximate the function of my weird brain. Functions are arbitrary mapping between things, and there is always a neural network that works. The problem is, there are also an infinite number of functions. There are an infinite number of functions for any given finite set of data. So if I give you 10,000 data points, you might think, I am able to precisely locate the neural network that predicts my function. But the problem is that there are an infinite number of my functions. Just because you have one in mind doesn't mean that that's what the neural network is going to learn. So I think I have a plot somewhere where, here we go. So this is 4 data points. And the human being obviously looks at this and says, well, the straight line is obviously the truth. But each of these different curves, this orange step function here, this wibbly-wobbly one here, these are all valid functions that could have produced these 4 data points. And with 4 data points, you have no idea which one it's producing. And you can add an infinite number of data points. You will never be able to precisely locate your function. It might just be a function that, for the data you've given it, gives the same output. And I think this is a fundamental problem for explainable AI. Because you don't know what your function is. You've deliberately designed this entire black box network where I gave you a bunch of equations that also magically happen to produce to this, to me, very simple, potentially not to you, very simple formalism. But you never, ever have a guarantee that what you've produced is anything like what you think it's doing. Right? My cuteness prediction, accurately, with 100% accuracy, produced the predictions I agree with. but it also told me that lions, no, what I tested it on? I trained it and it told me that, oh, it told me my cat wasn't cute because I actually went and measured, my cat's got longer fur than average. And it told me my cat wasn't cute, which is obviously wrong because, as again, I'm not sure if you've gathered this, my cat is very cute. So you never know whether these machines have learned something generalizable. We hope when you do these big transformer networks or you do these big, variational autoencoders, we are hoping that in some way the network has abstracted, has generalized some kind of features. But that is all it ever is. It's a hope that it has done that. And Explainable AI is about trying to tease out what those abstracted features are. What has it actually learned? And unless you're doing something where your network is a lot more constricted and restrained than the general frameworks that we've presented here, that is a doomed endeavor. You can try and do things like Shapley analysis and try and say which of my input parameters is more important, but that doesn't actually tell you anything about the function which you are approximating. And that's a big problem that we need to try and work out how to overcome. My personal opinion, and as the person standing at the front, that means it's the right opinion, is that we need to design networks from the ground up so that you control that this node is trying to predict this thing, but that requires basically rebuilding the entire formalism from the ground up. And again, a lot of the reason why this stuff worked was because it was so simple to implement. And as soon as you start breaking that, things get more complicated. So it's a big challenge that obviously we're hoping to have solved by the end of this conference, right? So those are the sorts of things that we have to deal with. That being said, this is a very complicated function that if any of you had cracked open the complex classifier or the complex function, that if you try and plot this function, you get something that looks something like that. So on that note, thank you very much. Well done, everybody, because that was a difficult set of challenges. I hope you go home and I hope you've learned something about the sort of intrinsic maths and the intrinsic sort of formalism that's going on, and why that means that the challenge of understanding why these things are making the decisions that they're making is quite so difficult. So I look forward to seeing what everyone else has to say over the course of this conference. And there's a picture of my cat.
Good afternoon, everyone. I think we're at the afternoon. Yeah. Just to let you all know, we've got lunch that's going to be served now. So whenever you're ready, you're welcome to leave your laptops here if you're staying for the afternoon. Lunch will be out this door, and then to the right, if you just follow the auditorium round to the right. Okay. We have got another session on this afternoon. It's starting at 1:30 until 4:30, where we're going to have Simon and Max, and they're going to be talking about the integration between dry lab and wet lab, and how kind of the work that they do fits into that as well. Okay, so we hope to see you there soon. If you do need to head off, that's no problem as well. Could we give Jack another round of applause, please? And anyone joining us from YouTube as well, if you head over to the next link at 1:30, we'll see you in the next workshop as well. Okay.
And just to confirm that all the notes, everything will be on the GitHub for all eternity, so you have all the time in the world to look at them. So